Good morning and welcome to NHP's public webinar series. Our subject today is the very broad subject of selectivity. As we're only taking 30 minutes at a time, this will be the first in a series of 4 on selectivity. The topic seems a simple, straightforward one. However, when we look at selectivity in all of its levels and definitions, it can be a very complex subject to understand. This webinar covers the basic aspects of circuit breaker selectivity. We'll explain the meaning of selectivity and some of the expected behaviours of the protection. We discuss expected fault magnitudes, types and behaviours. We'll discuss prospective fault current, how it's calculated and how it's derived. We'll also look at the regulations according to AS NZS 3000-2018 and definitions according to AS NZS 60947 Part 2, 2015. Selectivity has replaced discrimination in the standards literature. Selectivity in our electrical system is achieved when the system and protection components are chosen and arranged so that in the event of an electrical fault, only the device closest to the fault will interrupt the current flow, leaving the upstream devices closed to allow reliable supply to be maintained to all unaffected circuits. So in practice, how is this achieved? Quite simply, when a fault occurs downstream of the second or third breaker in a series circuit, the current that flows is common to all breakers in that series circuit. So, given the position of a fault is at F, the same magnitude of fault current flows from the source through breaker A, through breaker D, and into the fault site. The trip level settings in a time and current coordinate that cause breaker D to react and begin opening, and the speed of total clearance of the fault by breaker D will determine how breaker A behaves. If breaker D is too slow to react and too much let-through energy, normally expressed as I squared T or current squared by time, flows in the circuit, breaker A may also open. When we're discussing time current selectivity at low levels of current and an upstream breaker tripping due to overload of the downstream system, we're talking about a different issue. We're normally talking about a diversified system overload, and this is not covered by selectivity. Selectivity only refers to devices in a single line or a series circuit. So why selectivity? Quite simply, if we use selectivity smart, it can give us a possible reduction in costs in commercial and industrial applications. Give us reductions in switchboard sizes, and most of all, it can give us an increase in reliability of supply. Prospective fault current. We're going to mention prospective fault current many times as we work through the concepts of selectivity. Prospective fault current is the maximum current that can flow under fault conditions in an electrical circuit. Ultimately, in electrical design, we must ensure safety and integrity of the system and equipment to withstand the highest level of fault possible should there be a short circuit event. Fault current is expressed in Ka or thousands of amps. It's determined by the supply source capacity. It's regulated by the latent line impedance from the source to the point of calculation in the installation, and this can be at any point in the electrical system. We always assume it to be the worst case scenario calculated on a zero impedance bolted short circuit fault, which we'll explain a little bit later. The table shown here illustrates the possibilities of prospective fault current given an upstream low voltage transformer size, assuming an unlimited upstream supply and an internal build characteristic of the supply transformer. As an example, given a 3-phase transformer, let's say 11 kV to 400 volt, and a low voltage capacity of 500 kVA for the transformer, we have around 700 amps nominal full load current of the transformer. Given a 4% internal impedance of the transformer, a maximum of 17,000 amps or 17 kA can flow into a three-phase bolted fault. The figures shown are levels available at the secondary supply terminals of that transformer. We can see here different levels of fault current available with different internal impedances and different sizes of transformer. As we reticulate away from the transformer, the conductors of a particular material, let's say copper or aluminium, their cross-sectional area in millimetres squared and root length will give us a reduction in the prospective fault current due to the impedance of the materials. For example, if we take a 95mm squared copper cable and run it along a 49-metre root length and calculate the prospective fault current at the end of that cable, given a 30 kA prospective at the beginning of that cable, approximately 12 kA will be available. Smaller conductors and longer root lengths will further reduce this figure. Conversely, larger cables, parallel cables, and shorter root lengths will increase this 12 kA figure. Here's a simple design showing the source of a 500 kVA transformer. Has a 3.9% internal impedance factor, a supply capacity of 721.7 amps roughly. It has a prospective fault current at its three-phase terminals at 400 volts of 18.5 kA. If I connect 10 metres of 400mm squared to run to the main switchboard, fault current at the main switchboard is reduced to 17.2 kA. I run a line of 20 metres of 120mm squared to distribution board 1. The fault current at DB1 is reduced to 14.2 kA, down from 17.2. Compare that with running the same size cable, 80 metres. Run that to DB2 as an example, the fault current is reduced to 8.8 kA. This is a simple demonstration of increased latent impedance and the effect of the prospective fault current at different points in the installation. So let's define an electrical fault. An electrical fault is the current flow that's unexpected, dangerous, or outside of system design parameters. That's a fair indication, that's a fair definition of what a fault current is, an electrical fault. So let's have a look at a couple of the different types of faults that we can expect in our system. The types of electrical fault include earth leakage. Now, earth leakage is never considered in selectivity calculations, but earth leakage will be covered in another webinar, I'm sure. On circuit overload, I've chosen a nominal figure of around about 150% of the nominal fault over the nominal current rating of the circuit. And let's say it occurs for over a long period of, let's say, around about an hour. Shock loads or inrush, a nominal current rating of say 4 to 20 times the nominal rating of that circuit. This is not a fault, it's just a consideration. It's a consideration of the protection equipment we need to look at to withstand that shock load inrush. The breaker should not trip under these conditions. We look at earth or ground fault. We look at a nominal circuit current of 10% detected flowing to earth. Now, this is normally detected by other equipment. A standard circuit breaker would not need to trip under these conditions. We look at arcing fault. Arcing fault generally has a prospective fault current to detect between 10 and 50% of the prospective fault current. and bolted short circuits. Bolted short circuits, worst case scenario, we can expect a prospective fault current of 100% of the potential. Let's look at the potential when we look at different between different phases. A three-phase bolted fault will give us a 100% of the prospective fault current delivery. Two-phase bolted faults will give us around about 87% of the prospective fault current delivery. Single-phase bolted faults, of course, root 3, or 68% of the prospective fault current delivery. The type of fault can reduce this number to a very low level. This being the case, for high-risk applications, the system needs careful analysis, and the components chosen need to have specific behaviours to cover all contingencies. Let's look at some of the definitions contained in AS/NZS 60947 Part 2. Clause 2.17.1 defines overcurrent selectivity as the coordination of the operating characteristics of two or more overcurrent protective devices, such that on the incidence of an overcurrent within stated limits, the device intended to operate does so within these limits, while the other does or doesn't. This is a simple and basic definition of what is expected for simple overcurrent selectivity. Clause 2.17.2 defines total selectivity as the overcurrent selectivity where, in the presence of two overcurrent protective devices in series, the protective device on the load side affects the protection without causing the other protective device to operate. So it fairly much covers or follows simple overcurrent selectivity. However, it defines that this is up to the full level of the expected fault, called total selectivity. For the next definition, we need to understand a couple of points defined in the standard. The terms ICU and ICN. ICU is defined as the interruption capacity ultimate, according to device withstand testing to AS/NZS 60947 for industrial type circuit breakers. These are circuit breakers that are designed to be maintained or operated by trained staff. ICN is the equivalent testing done to AS/NZS 6098 and is for domestic type circuit breakers. These are circuit breakers which are designed to be operated by unskilled or untrained people. ICU and ICN is the maximum fault current the device can interrupt safely, twice for ICU or 3 times for ICN. There are different standards and different test criteria contained in both of those standards, but this is what they need to withstand ultimately. So full selectivity can be achieved up to the ICU or ICN of the downstream device, or the prospective fault current at the point of the installation of the downstream device. This means that if we define full selectivity, the expected behaviours of the device means that the downstream device will operate up to its ICU or ICN, but the upstream device will remain closed. Partial selectivity is the overcurrent selectivity where, in the presence of two overcurrent protective devices in series, the protective device on the load side affects the protection up to a given level of overcurrent without causing the other protective device to operate. If we understand up to a given level of overcurrent, this means that we don't have to specify that the downstream device operates only and the upstream device remains closed up to the prospective fault current level. It only means that the downstream device will operate under part of that selectivity criteria. So above this level, both devices may trip. So up to our partial selectivity nominated level, both devices may trip, but the prospective fault current level must be below the ICU or ICN of the downstream device for this to be a relevant definition. Let's look at the term cascade or backup protection. Cascading is achieved when the upstream device assists the downstream device to interrupt a fault current higher than its designed fault current limit, ICU or ICN. Now, the cascade level is the point where the upstream device also operates and assists the downstream device to interrupt the fault. So like formerly fuse protection, where the fuse used to back up the downstream device to a higher level than its rated fault current interruption level, the upstream device or the upstream circuit breaker here also assists the downstream device to break a higher fault current level than its rated ICU or ICN. This is called cascade protection. This takes us to the next subject of enhanced selectivity. Now, we're not going to cover enhanced selectivity in great detail here because it starts to get us into many of the complex applications that will take way too long for this webinar, and we'll cover this in future webinars. But as a definition, enhanced selectivity is achieved when the upstream device assists the downstream device to interrupt a fault current higher than its designed current limit or ICU or ICN. The upstream device will achieve this without tripping up to a nominated level above the downstream device's ICU and ICN. This is an important thing to understand, but we'll cover this in future webinars. Let's have a look at characteristic curves, time current curves of devices. Seen here, we show a main switch, a 40 amp single phase main switch with a C curve, and the downstream sub-circuit is a 6 kA 20 amp C curve breaker. We see here the thermal or overload section of the curve, and shown here is the short circuit section of the curve or the instantaneous section. The example shown here is a single phase domestic type scenario where the upstream is a load center main switch of 40 amps C curve, and the downstream is the final sub-circuit 20 amp C curve. We can see that the breakers do overlap slightly between the 3-second and 20-second time coordinates at overcurrent values between 75 and 200 amps. This means that selectivity theoretically can only be achieved up to 75 amps. Above this level, given an overcurrent, the upstream main switch may also trip. There are many levels of fault that need to be considered if we are to increase our system supply reliability. To that end, we look at DIN breaker curve designations. So when we're looking at DIN breakers, we have various trip curve types. We have B curve, C curve, and D curve. All of these curve types share the thermal curve characteristic, but they differ in their instantaneous trip points. B curve instantaneous trip value is between 3 and 5 times its nominal curve rating. So, for example, if we have a 10 amp B curve breaker, its instantaneous trip point will be between 30 and 50 amps. These devices were designed to be used in applications where there were long cable runs and it was necessary to interrupt a low level fault current in a much quicker time. Long cable runs, generally in applications like car park lighting, sports lighting, and when we're talking about very long cable runs when we're talking about motor starting in let's say petrochemical applications. C curve has an instantaneous trip value between 5 and 10 times IN. C curve is a general purpose trip curve, and they're suitable for the normal domestic, commercial and industrial applications. They can be used in most applications, even most motor starting applications. D curve is between 10 and 20 times IN. These breakers are suitable for applications where the connected loads have a high inrush or startup characteristic. Loads such as iron core transformer fed devices, HID lighting and LED driver loads, welders and some specific motor types such as IE3 and later models. They're also used for small capacitor applications. These trip characteristics can have a bearing on their use and suitability for applications where selectivity is required at the instantaneous level as well as the thermal time current level. Let's have a look at ASN ZS 3000 2018 in respect to the downstream device's current rating and what it says. For current ratings of the downstream device greater than or equal to 800 amps, discrimination or selectivity shall be provided by a coordinated study using manufacturer's data. The time current coordinate sheets that I showed you a bit earlier is a screen print of NHP's 10 curve selectivity program, and along with data which has been produced in table form, this is what the manufacturer's data is referred to in AS 3000 as a need to be referred to above 800 amps. For current ratings where the downstream device is greater than 250 amps and less than 800 amps, discrimination shall be provided between overload curves and is deemed to comply if the upstream setting is 150% of the downstream device time current setting. For example, 600 amps to 400 amps is a 150 amp difference, 150% difference. For current ratings of the downstream device less than 250 amps, discrimination is deemed to comply if the upstream device is 150% of the downstream device's rating. So in the example I've given here and is shown in AS 3000, 63 amps to 40 amps. However, Amendment 1 states that selectivity is not mandatory for downstream circuits 80 amps and under. Now, not being mandatory doesn't mean it's not desirable. So depending on what the use of that downstream circuit is, selectivity may be a desirable factor, even though to AS 3000, it's not a mandatory requirement. If I have a look at the selection pre-Amendment 1, we have a look at compliance to 63 to 40 amps to the wiring rules. And we see here, by mistake, we see here that the requirement for AS 3000 shows a time current coordinate where we start to have conflict in the time current curve and the instantaneous curve. So there is no guarantee that this combination will comply in all respects. The width of these curves is the allowable tolerance. Generally speaking, there will be a single line within these curves, which is the median trip point of these devices. However, a tolerance is allowed within these devices. If we allow full selectivity in a domestic application or a small application, shown here is a 63 amp device, C curve, and a 20 amp RCBO, C curve as well. We see here that there is a clear difference between the time current curves, and we can guarantee selectivity in this respect up to the instantaneous level of the upstream device. The instantaneous level of the upstream device, of course, is an average of 7.5 times our 63 amps for a C-curve device. So this is what a typical domestic application would look like. So let's summarise. AS/NZS 3000/2018 nominates only the minimum level of supply security required. Only the minimum level of supply security required. Certain installations may require high levels of security to supply. A risk analysis or consequential outcome study needs to be done to understand what supply behaviours need to be adopted for any particular installation or circuit. Prospective fault currents need to be determined and understood for safe, functional and compliant installations, and to also understand what the behaviour of the devices installed in those installations need to look like. Selectivity is a word. It's not completely definitive. Selectivity describes a behaviour. Specific levels of behaviour given specific currents expected from faults that may occur need to be nominated. This will help determine system reliability levels. Circuit breaker behaviours above their time current characteristics may only be determined under test conditions, breaker for breaker. In these situations, we can only confirm performance when we consult a manufacturer's test data. Often this will limit the choices of devices to one manufacturer. This first presentation has been fairly simple, demonstrating some basic information and scenarios. We've explained a little about what selectivity is, some definitions of various terminologies and levels of fault we can expect in real terms. We've also covered the basic requirements for standard selectivity conforming to AS 3000/2018. Future webinars on this subject will become increasingly complex and challenging. We trust you're able to gain some information from this first in this series and look forward to you tuning into our future webinars on this subject. Please type your questions into the dialog box along with your email address, and these will be followed up and answers sent to your email. Thank you for your interest and stay safe. I'll be on the line for the next 5 minutes to answer any of your questions live, or email me at syoung@nhp.com.au. Thank you.
Hi, Steve. It's Shane Townsend from NHP here. We've just got a few questions that we've published. Are you all right to answer them if I read them out to you?
Sure, Shane, please do.
Okay, so we'll start from the top. Rodney Townsend has asked, is there a difference between the formulas for calculating 3-phase and 2-phase and single-phase faults?
Yes, there are. There are different factors to come up with different answers, of course, and with they're fairly complicated calculations. But yes, in answer to the question, there are, and there are many examples available on the net and through the standards.
Thanks for that. We've got a few here, so there's probably about 5 or 6 to go through that we've published.
Sure.
Do we still reference the ICS, the interrupting capacity service rating?
ICS 60947. You'll notice that the ICN rating to 60898 asks for 3 tests: the open, close, open, close, open. This is very, very similar to the ICS rating of the 60947 test for industrial breakers. So yes, we still do reference that as an ICS as the service rating.
Thanks for that. We have another one. This one comes from Charville. He's asked the question, if my distribution board fault current is rated at 14 kA and I have used a 15 kA circuit breaker as the main breaker, can I then use 10 kA breakers downstream at that distribution board? If the fault current goes above 15 kA, will the main upstream 15 kA breaker protect the other 10 kA breaker?
Thanks for your question, Shah. The answer is no, or the answer is maybe, and I'll explain maybe. Maybe means that you need to refer to the manufacturer's data and ensure that the upstream device still affords protection to the downstream device in that distribution board. Just because it's 15 kA itself is protected, but the 10 kA device downstream may not be unless it demonstrates either cascading behaviour or selectivity behaviour and protection behaviour to the downstream device. In other words, enhanced selectivity behaviours between the two breakers, only available via manufacturer's test data.
Great, thanks for that. We have one from Ben here. He has heard some feedback that type B miniature circuit breakers trips easily and are bound to have more nuisance tripping than when people would use a C-type miniature circuit breaker instead. He's just asked for an opinion and some general comments on that. So the B-type nuisance tripping more frequently than the C-type miniature circuit breaker.
Absolutely correct. That's because of its characteristic of an instantaneous trip point that averages around about 4 times its nominal rating, whereas a C curve is about 7.5 average on its nominal rating. The B curve should really only be used under specific circumstances where we have an issue with earth loop impedance and slow or low fault current tripping characteristics, and there's no need to use a B curve on most applications. As soon as we start to use devices that trip more quickly, don't forget our prime purpose is to protect conductors, nothing else. It doesn't protect equipment very well, only conductors. So as long as your conductor is able to withstand the fault currents and overcurrents events that we require, use the correctly rated circuit breaker for that application, unless of course it's mandated in the standards to use it for a different purpose, earth loop impedance purposes.
Thanks a lot, Steve. That's probably all the time we have today for questions. So we can see there are some other questions that have come through. We will address them via email. A lot of people have asked if there will be a recording. Yes, the same webinar site you use to register for this will have recording of this webinar, as well as other webinars that you can find there pre-recorded, and all our future ones coming up as well. So on that note, yes, we will leave the questions we didn't get to be addressed privately via email. Thanks a lot.
Thanks everybody for tuning in.